Welcome to our course on mastering numerical method for partial differential equations with MATLAB. In this lecture, we will delve into the explicit and implicit time stepping methods, which are fundamental techniques for solving partial differential equations numerically. Explicit methods compute the state of a system at a later time based on the state at the current time, offering simplicity and ease of implementation, but often requiring small time steps for stability. In contrast, implicit method determine the future state by solving a system of equations involving both current and future state, allowing for larger time step but at the cost of increased computational effort. These methods are essential in various scientific and engineering applications where modeling dynamic system accurately over time is crucial. Let's delve into the lecture. Here in this lecture, first we are going to cover the basic introduction about explicit and implicit time stepping methods for partial differential equations. Partial differential equations are the fundamental in modeling various physical phenomena, including fluid dynamics, heat transfer, and wave propagation. Solving these equations numerically often involves discretizing both space and time. Time stepping methods are crucial for advancing the solution through time. Two primary categories of time stepping methods are explicit and implicit method. In explicit time stepping method, the solution at the next time step is calculated directly from the known values at the current time step. These methods are straightforward and easy to implement. Here we have the very simple example, which is a common explicit method, forward Euler method, which is defined in the equation number 1. Here on the right hand side, we can see that when t is equal to tn, we have un. So these both are known. Okay. And on the left hand side, we have u raised to power n plus 1, which is unknown. So this is unknown, this is known, and tn is also known. So this type of the equation, which the left hand side is dependent on the right hand side, and all the variables on the right hand side are known and or independent. So this type of the problems are known as explicit method, and forward Euler method is one of the most important example. Here we can see one more example, which is Rankata method and higher order explicit method that improve the accuracy. In this method, we can observe that when we have t is equal to tn, this value is known, and all these values k1i, k2i, k3i, k4i, this is Rankata method of fourth order. Okay, all these values will be computed from these equations, and the left hand side, which is ui n plus 1, this is unknown, this is unknown, and all these values are known on the right hand side. So these are on the right hand side are independent, and the left hand side, which is ui n plus 1, this is dependent. So this is the another example for explicit method, and in this method we have uin is the numerical solution at special point I, and time level is n, h is time step size. Okay, so these are the two examples for explicit method when the left hand side is dependent and on the right hand side we have all independent variables. What are the advantages of this method? This method simplicity in implementation and computationally inexpensive per time step is they do not require solving a system of equations. And disadvantages: stability constant, notably the CFL condition, which restricted the time step size. Delta t less than and equal to, delta t is less than and equal to c delta x upon v. Delta x is the spatial step size, v is the characteristic speed of the system, c is constant. Applications of explicit method suitable for problems where the time step size can be small enough to satisfy stability criteria, such as wave equation and advection dominated problems. Next, we have the most important method is which are involved implicit time stepping methods. Implicit time step method involves solving a system of equations at each time step. The solution at the next time step depends on both the current and the future state. For example, we have the two common implicit methods which are described in equation 3 and equation 4. And from these we can easily observe that on the left hand side we have is un plus 1. This is the current time which we need to define, we need to calculate, and un, when we have t is equal to tn, this value is known, and but this function, this un plus 1 and tn plus 1 both are unknown. Okay, so the left hand side is unknown and right hand side is a mixture of known as well as unknown. So this type of the problems are known as implicit. This type of the problems, when we solve, we required implicit methods, and backward Euler method is one of the example. And similarly, we can see in the next method, which is Crank-Nicolson method, which can be used. And here you can see that in the case of Crank-Nicolson method, second order accurate method that averages the explicit and implicit update. On the left hand side you can see that this is unknown and un is known. Okay, this is known value. Again, this will be known and this is unknown. Okay, so in this case also there are so many problems. According to that, we have to choose whether we need to apply backward Euler method or Crank-Nicolson method, or in the case of we have the problem which is associated with explicit problems. Okay, so according to the choice of the problem, we have to choose the method, and also we need to compare the result, which method is more appropriate, and return the correct solution. Advantages of implicit method: unconditionally stable for many linear problems and allows larger time step. Disadvantages: more complex to implement due to the necessity of solving system of equations at each time step. And secondly, computationally more expensive per time step. What are the applications of this method? Ideal for diffusion dominated problems and stiff system such as heat conduction and some reaction diffusion equations. Here how we can choose or choosing between explicit and implicit method. The choice between explicit and implicit method depends on several factors, including the nature of the partial differential equation, desired accuracy, computational resources, and stability requirement. So on the basis of these parameters, we can decide which method is required or we can implement. Just like we have the explicit method, preferable when simplicity and low computation cost per time step are critical and when the problem is not stiff. The second implicit method is applicable when necessary for stiff problems and when stability is a major concern, allowing for larger time step and potentially a faster overall computational despite the higher cost per step. Here we have the comparison between explicit and implicit method. On the first column we can have the accept, in the second column we have the explicit method, and in the last column we have implicit method, and here we will compare. This will help you to choose the method, which method we can apply, and also this will help you which method are associated with the explicit method and which are associated with the implicit. So formulation, as we can see that the left hand side which is independent and right hand side will be completely, here we can see that the right hand side is completely independent and left hand side will be dependent. And in the case of implicit, this will be the mixture of dependent and independent. G will be the some function of u raised to power n plus 1 and un is equal to 0. Okay, so this will be the mixture of dependent and independent. Some function will be on the right hand side. Stability, explicit method depend upon the conditionally stable, which is CFL condition, and implicit, these are unconditional stable. Time step size in the case of explicit method requires a small time step for stability, and in the case of implicit method, user can use larger time step for this implicit method. Computational cost in the case of explicit method is less computationally expensive per step, but in the case of implicit, we have more computationally expensive per step. Implementation, this is easier to implement in the case of explicit method, and implicit methods are more complex implementation. Solution process, explicit method we can directly implement to compute, when implicit method require solving system of the equations. Applicability, suitable for non-stiff problems, and implicit method are useful for stiff type of the problems. Examples or the methods for explicit method are, as we discussed, one is forward Euler method and second is explicit finite difference method, along with we have the Rankata method. And in the case of implicit method, we have backward Euler method, and second is Crank-Nicolson method can be used for implicit type of the problems. Accuracy, implicit method can be less accurate with the larger time step, and implicit method can be more accurate with the larger time steps. So that's why in the case of stiff type of problems, we can easily implement implicit methods are more accurate. Iterative solver not required, and in the case of implicit method often required, and memory user in the case of explicit method generally it will be lower, but in the case of implicit method it is higher. So these are the some common difference between explicit method and implicit method is described in the table, and these differences will help you to choose the method, whether we need to apply the explicit method or we need to implicit method. In conclusion, we can say that the understanding the difference between explicit and implicit time stepping methods is crucial for solving partial differential equations effectively. While explicit method offer simplicity and efficiency, they are limited by stability constraint. Implicit method, although more computationally intensive, provide stability advantages for stiff problem. The choice of method should be guided by the specific characteristic of the problem at hand and the computational resources available. So this is all about the basic introduction about these implicit and explicit methods. In conclusion, mastering explicit and implicit time stepping method is vital for effectively solving partial differential equations numerically. Through this lecture, we have explored how explicit method offer simplicity and ease of implementation while requiring smaller time steps for stability, and how implicit methods, through computationally more intensive, allow for larger time steps and greater stability. These techniques are indispensable in accurately modeling and solving dynamic systems across a wide range of scientific and engineering applications. By understanding and applying this method, you will be well equipped to tackle complex partial differential equation problems with MATLAB, bridging the gap between theoretical concept and practical implementations. Thank you to see this lecture till the end.